be 5 minutes early, so we'll end maybe 5 minutes early. So they say. Okay, let's go from current slide. And Bill was here to hear the announcement. The first class, I don't think you're interested in this one either, and he can listen if he is. But there are summer research experience for undergraduates available. One's at UAB here. I've got the information if you want to look into that. There are other schools that do. I believe they're posted out there either on the student suite, on Blackboard, or somewhere. They have a lot of these, so you can look and see for yourself. Okay. So, is that where we're beginning? Variation of parameters of page 159? Say again? Okay. Okay, 151? Okay. We finished 4.4, I believe, didn't we? And that ended about 151. Yeah. 152 is undetermined coefficients, the annihilator approach. There are two approaches to undetermined coefficients. We did superposition principle, and we're basically supposed to do either one, the superposition approach or annihilator. I've taught them both ways, and it seems like students like the superposition better. Seems like it's generally easier to understand. So that's why I'm skipping 4.5. It does the same thing, but from a different perspective. It's just a different approach. If you go through and read and you like it better, use it. Okay, perfectly fine. So 4.6 then is variation of parameters. Okay? Now, they said, we pointed out in discussions section 4.4 and 4.5 that the method of undetermined coefficients has two inherent weaknesses. Now, I don't remember them pointing this out. Maybe they said it, okay? That limits it wider application to linear equations. The differential equation must have constant coefficients, and the input function g of s must be of the type listed, remember, being exponential function, a polynomial function, a sine or a cosine function. I think that was it. Okay? Can't be log, can't be tangent, can't be inverse sine. Nothing is, it's limited to those. Okay? And the coefficients have to be constants. Okay? Now, in this section, we'll examine a method for determining a particular solution y sub p of a non-homogeneous or non-homogeneous linear differential equation that has, in theory, no such restrictions on it. This method is due to the eminent astronomer and mathematician Joseph Louis Lagrange, okay, known as the variation of parameters. And before examining this powerful method for higher order equations, we revisit the solution of linear first order differential equations that have been put into standard form. I know it is. Okay. The discussion under the first heading in this section is optional and is intended to motivate the main discussion of this section that starts under the second heading. Okay? Now, what this is basically going through how we got our integrating factor. I don't think there's anything else there. Okay? Now, when you get down to about 2/3 down the page, they mention variation parameters. As a means of motivating a method for solving non-homogeneous linear equations of higher order, we propose to derive a particular solution, okay, just like they were doing earlier, by a method known as variation of parameters. Okay? Suppose that y1 is a known solution of the homogeneous differential equation. Okay? There it is. The dy1 dx is equal to p of x y1, plus p of x y1 is equal to 0. Easily shown that y1 is equal to e to the minus integral p of x dx is a solution of that equation. Okay? Because this equation is linear, c1 y1 of x is its general solution. Variation of parameters consists of finding a particular solution of 1, which is up there at the top, okay, of the form, the particular solution y sub p is equal to u1 times y1. In other words, we've replaced the parameter c since I don't have my glasses, I can't see the c anywhere in here. Oh, I guess I mean the c is in c1. Yeah, the parameter c1, so I couldn't read it, by the function u1. And then substituting yp is equal to u1 y1 into the first equation, using the product rule, goodness gracious, I'm having trouble reading this print. The subscripts are so tiny. The sought after particular solution is that y1 that we got before times the integral of your f of x, which is your solution of the first equation, the non-homogeneous part, okay, divided by y1 of x, okay. Now,
question.
Yeah.
Okay, we got a particular solution that we have to find some function u1 is a function of x, and then multiply that by y1, which is a function of x. Then, if we go down to about page 80, and say you have to substitute the particular function, are we going back and say we have to find a particular function first, and then go through the steps of what they're saying, multiply multiply this to get a variation of the parameter?
Okay. Where I think they're being, I feel like the pot calling the kettle black to say they're being a little sloppy, because you know I'm sloppy. But I think they're being a little sloppy because there's two particular solutions. The top one, in the first part, is the particular solution of the non-homogeneous equation. Okay? I'm sorry. Okay, I'm sorry. I misread something. That there is a particular solution there, and if you see, their y sub c, which they used to call the complementary solution, I believe it was, okay? Only this isn't quite the same type of deal as that was. But, well, yeah, it was. I mean, it's very close to the same. That's of the homogeneous part plus the particular part. And in the it seems like they're going around the circles, and that's I'm guessing that's where things get a little confusing. Okay. Here you have a linear first order differential equation like we did back in 2.3. Okay? Now, we got a integrating factor, and remember, it was you did the integral of p of x dx, raise that to, you eat it, remember, and then you took, plug that in, and it became part of your solution, and if you look at this, you see, I'm having trouble seeing it, seeing all the signs, but the C1 here is that integral that follows it, okay? I'm sorry, well, it's sort of like it is, only this is being added to it, okay? This is not, this is keeping everything sort of abstract. They're not telling you what the x is or the p is, so you're having to carry around all the integrals and stuff, okay? The f of x or the p, okay? Now, this is your y sub p, that first part. I mean, y sub c is the first part when the f is 0, and then the second part, that's your y sub p, okay? Now, then this part here is y sub p. That's all it's saying. It's breaking this down into there's your complementary part, there's your particular part. So we're coming down here and saying we're going to start over and say that we know a y1 for the complementary part, for the homogeneous part. Well, that's what we're calling yc up here. We're calling y1 down here. And then, if when they change the blue, that really gets my eyes going crazy. So the y1 is the same thing that we call yc up here. You'll see it's exactly the same, except it doesn't have the C1 in it, okay? Well, and then they put it in it on the next line. Then the y sub p, they're saying let C1 be this U1. And then that's multiplied by y1, okay? Which is the function that you supposedly know is the answer for that one. And then you go through the same type of deal that you did with the other, and it comes out just about like, again, this is hard to see, so the y sub p is your u1, y1, which was your, basically, sort of like your y sub c before. And on this one, well, no, I'm getting, I can't keep up with my signs there.
Replace the parameter C sub 1 by the function of the U sub 1.
Right. And then they figure out the U sub 1 is this integral of F divided by Y sub 1. Which, yeah.
Don't remember this.
Huh?
Don't memorize this.
Okay.
All of the blues go right by.
Yeah.
Wherever they say you sub 1, plug it in.
Okay. This is supposed to help you see what they're going to do next. Let's look at what they do next and see if it makes sense on its own. And if it does, then maybe we'll see where this helped to that. If it doesn't, we'll just do it the way it says here. This is going to give us the way that we say we're going to. But now, of course, this is linear first order. Okay? The second part here is linear second order. Okay? And you got a lot of slugging here to go through and rearranging and stuff like this, that hopefully you'll see how the answer comes out, and then you don't have to slug anymore. You can just go back and do what is required without the complexity of having to figure out where all the pieces came from. You know, keeping up with the pieces, I guess, is the better way to say it. Let's see if we can. If we can just pick up here at linear second order differential equations on page 161. Okay? And maybe the first part will make more sense. So let's consider the case of a linear second order equation. Okay? Let me get my pen set up. Sorry, I didn't bring my glasses. My eyes are just really getting tired. A sub 2 of x times your y double prime, second derivative, plus a sub 1 of x. Now they're starting this very generic, okay, times y prime, plus a sub 1 of x times y, no, a sub 0 of x, we already used a sub 1 of x, times y is equal to some g of x. So linear, second order, non-homogeneous differential equations. Now, how does this differ from what we were doing before? These are functions of x. They're not constants anymore. If they're constants, you use undetermined coefficients, okay? Whatever it takes, okay? If they're constants, if they're variable functions, that's where we get our problem, okay? And we're non-homogeneous on top of that, okay? Now, although, as we shall see, the variation of parameters extends to higher order applications, not just to second order. But we're just going to deal with second order now and let it extend later. The method, again, begins by putting this equation into another form. Okay? What we're going to do is divide everything by a2 of x. Now, time out. a2 of x cannot be the zero function. If it were the zero function, you have a linear differential equation, not a quadratic, right? Not a second order. It's linear, because if a2 of x was 0. So a2 of x can't be 0 for any value of x. So therefore, it's legal to do this. You can divide by a2 of x. So we'll divide this one by A2 of x. We'll divide this one by A2 of x. And we'll divide this by A2 of x. Because A2 of x is not 0 for any value of x. So that's legal to do. So now we have a form that's y double prime plus, let's give that a new name. It's just a function of x. It's just not, you don't know what kind of function it is, it's just a function of x. And let's say, what will we call it? How about p of x? Y prime plus, how about q of x? Y is equal to, well, that's a new function too. How about let's calling that f of x. Okay? Now, it kind of looks like we're setting ourselves up for something like our linear form was. It's just that this single derivative, that y, and loses from altogether. Then we have exactly what we had in the previous example. Okay? And we can solve that by our linear method, which is integrate p of x, do all that kind of stuff. Okay. Now, all right. So in this form, we suppose that that coefficient functions p of x, q of x, and f of x are continuous on some common interval I. Now, especially since we divided by the same thing, if we did introduce a discontinuity, it would be the same for all of them. Okay? So, that's a fairly good assumption. You can find some integral under which this, and this are all continuous. Okay? Maybe a pretty small integral, maybe infinity, but there should be some interval over which they're continuous. Okay? As we've already seen in example 4.3, in section 4.3, there is no difficulty in obtaining the complementary solution. And of course, there was no difficulty. You just set the f equal to 0 and come up with that. No, never is it? Okay. So we'll do that and see what happens. Okay? But the deal is, the p of x and q of x were constants back then. They weren't, so I don't see how they can say that, because in 4.3 we weren't dealing with variable coefficients. Okay? But they say, as we've already seen, there's no difficulty in attaining that. All right. The general solution of the associated homogeneous equation of 6, when the coefficients are, now they put it in, when the coefficients are constants. Okay. Analogous to the preceding discussion, we now ask, can the parameters C1 and C2 in that complementary, so y sub c is equal to C1 y1 of x plus C2 y2 of x. Now, it was easy to get those if p and q were constants. Okay. Let's assume that they're not constants but variables, that we can still get something that looks like that. Okay. Sorry. The general form of the associated homogeneous equation of 6, when the coefficient, okay, we already did that. Analogous, okay. Can the parameters C1 and C2 in y sub, in the complementary solution. I'm sorry. I brought in my cough drops today. I swear, the cold is getting better and better and better every day over the break. Slowly, but better. Today it seems like it's just about like it was before. I don't know if the weather changed. I don't know. Anyway.
I'm sick of it too.
What's that?
I'm sick of it too.
Yeah. Well, I'm sick with it. Okay.
Yeah.
So sorry now I talk like I have rocks in my mouth, because I sort of do. Okay. We now ask, can the parameters C1 and C2 in this complementary solution be replaced with functions U1 and U2? So that's what they were doing before, was making that kind of a substitution, okay? Or variable parameters, which comes from variation of parameters. So here would be our particular solution. Y sub p is equal to u1 of x, y1 of x, plus u2 of x, y2 of x. Now, that's what we're going to attempt. To answer the question, can we do that? We substitute this thing right here that we just wrote down into our equation here, okay? And see what happens, okay? So what we've got to do, obviously, is take a derivative. Y1 of sub p is, and you got a bunch of product rules, so tell me what they are. U1 of x, y1 prime of x, plus, well, let's go on and do the other part. Y1 of x, u prime of x, plus u2 of x, y2 prime of x, plus u2 prime of x, plus y2 of x. Yeah. Okay?
It's hard to say.
I know. Now, we also got to take a second derivative. Now, that looks like it's going to be twice as long, except I think we'll find there will be some common terms. So let's give ourselves more room. Y double prime, yp double prime would then be, start with the first one, u1 of x, y double prime, y1 double prime of x, times y1 prime of x. That's the first one. Three to go. Okay. Next one. That's a y1. Okay. Let's do this one next, just to keep them together.
Oh, okay.
Got it? Plus
y1
u1 prime of x, right? Okay. Third one.
u2 of x times y2 double prime of x plus u2 prime of x
Okay, running out of room rapidly. That's the third one. And the fourth one is?
U prime of x.
Yeah, U2 prime of x. Wait, I put a plus sign in there. There's not one in there. That's a times.
Times y 2 prime of x. Plus u double prime u2 double prime of x. Y 2.
Okay. Now, my pen didn't write, so I wrote on top of something, so let me see if I can clean that up. There we go. All right. Now, let's see if we can combine any like terms. There's only the one U1. I'm going to start leaving off the x's. U1, Y1, double prime. Here's a U1, Y1, and there's a U1, Y1. So plus 2 U1 prime Y1 prime. Just in different order, but that's okay. And I think there's only one Y1 U1 double prime. Okay? That took care of all of those, didn't it? Now, this one is only one U2 Y2 double prime, but there's two of these, plus 2 U2 prime Y2 prime. That's these two. And then one U2 double prime Y2. Okay. Now, we don't need the top line anymore that I can imagine. If we do, I'll find it. All right. Now, okay. Now here's where I'm beginning to have some sort of an issue. Can y'all see a reason why didn't they combine like terms like we did? they chose not to. That's the side point. Now, when you substitute I see what you're saying. All right. Now here's the part that I find rather strange. I was going to say it earlier, and I thought I must just not be seeing something. Okay? What we were calling y sub p before is what we got when we put the f in at the end rather than 0. Now, what they're calling yp now is, remember, that's the complementary solution. That's the one when this is equal to 0. Okay? But that's what it was when these coefficients were constants. They're saying, well, if they're not constant, we're going to put variable substitutions in. But that's still leading that to be the homogeneous case. So this y sub p, whereas before you got the y sub p for the non-homogeneous case, this y sub p is still for the variable case, for the homogeneous case. Which, this is the thing that just sends my mind bonkers. This is not for this. This is for that, which was for that equals 0. Okay? And I look at that and say, you should have called it something else. I don't know what else, but I wouldn't call it P. Because the P to me is the part that you get from considering the non-homogeneous case. But this is not. This is putting this and that into C1 and C2, which still leads to the y sub c, which is the homogeneous case. And that's what they use in the next statement, which every time I look at it, I say, what are you talking about here? You know, this isn't the same y sub p before. This is the y sub p, you know, or the homogeneous case. Because what they say is, you'll see coming up, it's what they do. Okay, so what we're going to do is put this solution, the y sub p, into this equation here. Okay, so basically we're doing y sub p double prime plus p of x y sub p prime plus q of x y sub p. Okay. No, I'm sorry. Yeah, I'm sorry, I misstated that. This is still the non-homogeneous case. This is what they left off here. I'm sorry, this is where I messed up because I'm not seeing it well. The y sub 1s and y sub 2, these are the ones that are the homogeneous case. That would be when the f is 0. Sorry, the y sub 1 and y sub 2 are the solutions when they would be 0. Sorry about that. And then we're putting this U1 in for C1 to make the non-homogeneous case. I'm sorry. I can't read. I thought that was a P and that's a 1. Sorry about that. Okay. So let's do what we just said. And we know this is going to equal f of x, but let's not do that yet. So the y sub p double prime is U1 y sub 1 double prime Okay, I'm going to just go and write it all out like we did. Plus 2 u sub 1 prime y sub 1 prime plus y sub 1 u sub 1 double prime. Okay. Plus y sub 2, I'm sorry, u sub 2. Sorry about that. Y sub 2 double prime plus 2 u sub 2 prime y sub 2 prime plus u sub 2 double prime y sub 2. Okay. Changing the way we do it a little bit, but it's okay. I mean, the order is not. Plus p of x times y1 prime, yp prime, okay, which would be u1 y1 prime plus y1 u1 prime plus u2 y2 prime plus u2 prime y2. Okay? Plus q of x times y sub p, which is y sub p, which is u1 y1 plus u2 y2. And that's all supposed to be equal to f of x. Okay. Now, if we take a u1 out from here, u1 times. Now let's put here y1 double prime. Okay, that takes care of that term. Okay, let's go over to here and take out a u1 and a p of x, and this is we've already factored out the u1 plus p of x y1 prime. Okay? Now that takes care of this term with the p of x. Okay? Let's jump to the third one. Plus, there's the u1 that we've already factored out. Okay? And you've got a q of x y1. All right, that will take care of that term. All right, now let's do the same thing with u2 and plus a u2, and that's multiplied by a y2 double prime. Okay, that will take care of that term. And here's the u2 y1 y2 prime, okay, plus we already pulled out the u2, and you have a p of x from here, okay, times y2 prime, so that takes care of this term inside that parentheses, okay, plus pull out the u2, and you're left with a q of x y2. You already pulled out the u2. All right. All right. Now, we have other terms. Okay, taking care of that. What terms do we have left?
Two double prime.
Yeah, I'm still trying to find what they did. Seems like they're missing a term or so here. We came up with two of these, and they came up with only one. And I don't see where that happened. I'm having trouble seeing in the first place, but there's a U1, Y1, and another U1. U1 prime, Y1 prime, and Y1 prime, U1 prime. That's two of them. And then they have the same here. Y2 prime, U2 prime, plus U2 prime, Y2 prime. It's two of those. But they come down here and only show one of each of those. No, they list them, okay. No, they do list it twice. They just separate them. And there's a reason for it. So we'll get there in a second. Okay. I see no reason to separate, but let's see what we got. So I'm going to have plus here, plus 2 U1 Y1. That takes care of that one. Plus Y1 U1 double prime. That takes care of that one. Plus 2, these are primed here, I forgot, left off my primes. 2 U2 prime Y2 prime. That takes care of that one. Plus U2 double prime Y2. That takes care of that one. Plus, I'm going to continue here. Sorry, this is messy. A P of X. U1 Y1 prime. Let's see. Y1 U1 prime. Plus a P of X. U2 prime Y2. I'm going to call it Y2 U2 prime. That takes care of those two. Plus a Q of X. No, that's gone. The Q of X's are gone. Sorry about that. Okay. And all this thing is equal to f of x. All right. Now, here's where the kind of magic happens. Okay. Remember that this was your complementary solution. F of x equal to 0. Okay? C1, which is now U1, Y1, plus C2, Y2. And that's when this is equal to 0. Okay? But, and Y1 is the solution for that. Y2 is the solution for that. But Y1 is Y1 double prime plus P of x Y1 prime plus Q of x Y1, which is exactly that. Y1 double prime plus P of x Y1 prime plus Q of x Y1. But remember, that's the solution for your complementary. So this thing is 0. Okay? So this whole shebang here is 0. And this whole shebang, because remember, y2 was also a complementary solution, so that thing's 0. Okay? So what does that leave us with? Now they split them separately, and I have yet to figure out why. Okay, I think I do see why. Okay. Now, what we're going to do is remove the 2 here and the 2 there and put them in down here. Write them again. U1 prime, Y1 prime, plus U2 prime, Y2 prime. Okay. They wanted us to do that, so I did it. I succumbed. Okay. I don't know where to go next. I guess I'll erase this one. You got to remember what this, whoops, that's not what I wanted. Eraser. Okay. You got to remember this, but hopefully we do remember it. Okay? And if we don't, we'll go back and reproduce it. Okay? I don't know why my thing's not erasing. Maybe one of these days it will. There it goes. Okay. Let me start here. So when you eliminate those other terms there, what you have is a U1 prime, Y1 prime, plus Y1, U1 double prime, plus U2 prime, Y2 prime, plus U2, I can't read my writing here, that's supposed to be a U. A U there, U2Y, U2 double prime, Y2, plus P of X, Y1, U1 prime, plus P of X, Y2, U2 prime, plus the 2 we added back, U1, stinking thing, the pen won't write, and then I can't find where I wrote, okay. That's a plus, U1 prime, Y1 prime, plus U2 prime, Y2 prime. Okay, that's a U there. It looks like an A, it's not. Okay, and this is supposed to be f of x. Okay. Now, for some reason they do this. They say, no, this thing right here, these 2 terms, isn't that the derivative of d by dx of y1 u1 prime? It is, isn't it? That'd be y1 prime u1 prime plus y1 times u1 double prime. Okay. Why? Don't know, but let's do it again. Do the same thing to these 2, and that's d by dx of u2 prime y2. And I'm writing them backwards. I don't know why, but it is. But sure enough, that is the case, because this would be u2 prime y2 prime plus u2 double prime y2. So that's true. Okay? Plus, let's factor out the p of x, and that's times u1 prime y1 plus y2 u2. I've left off a prime somewhere there. That's u2 prime. Okay? Plus u1 prime y1 prime plus u2 prime y2 prime, and that's supposed to equal f of x. Boy, this is tedious. Okay, I'm going to have to do some more erasings. Hopefully we won't need this again. All right. You might ask yourself, why in the world do we need all that? Well, you can combine these, d by dx times y1, u1 prime, plus y2, u2 prime. That cough drop sure didn't last too long, did it? Okay, plus p of x times y1, yuck, u1 prime plus y2, u2 prime. Okay, plus u1 prime, y1 prime, plus u2 prime, y2 prime, equal f of x. Now, these are the arguments of a derivative. This is a factor of the p of x. Okay? And then that's just a combination. That's equal to f of x. Okay. Because we seek to determine two unknown functions, u1 and u2. We know the y1 and y2. That's from earlier, what I've erased already. Okay? But the u2 and u1, we don't know. Okay? That's what we're looking for. Reason dictates that we need two equations. We can obtain these equations by making the further assumption that the functions u2 and u1 and u2 satisfy this. Okay, here's the magic. I sure hope I don't need this anymore because it's long gone. Okay, here's our next assumption. I don't know what justifies it, but here's what it is. U1 and U2 satisfy this equation. y1, u1, u1 prime plus y2, u2 prime equals 0. Okay? Now, why in the world would that be a reasonable assumption? It sure looks nice, because the derivative of 0, which is exactly what this thing is 0. And p of x times 0, which is exactly what that thing is 0. And that would then leave us at that simple little equation there. Okay? Now, how can you justify this? I don't know. Okay? But let's see. Okay? This assumption does not come out of the blue, but is prompted by the first two terms of this. Well, yeah. Still look like it came out of the blue to me. Okay? Then this reduces, like I just said, to this thing equal to f of x. Okay? We now have our desired two equations, albeit two equations for determining the derivatives u1 and u2. Okay? So here's one equation, and here's another equation. Now, y'all haven't had linear algebra, but have you ever heard of Cramer's rule? Okay. How are we doing on time? What's that?
Just the guy on Seinfeld.
Oh, no, different one. I think, was he a KR or was he a CR? I don't know.
It was K, don't you?
Yeah, I don't know. And that was his first name or his last name? I don't know. Oh, here's the problem with me, and this sounds terrible. I never watched an episode of Seinfeld. I saw little things here and there because everybody was always talking about it, but I never saw an episode. Huh?
I watched a few, maybe like 30 of them.
What's that again?
I watched like 30 of them.
Oh, is that right? Okay. And it seemed like there were hundreds of thousands of them. I don't know. They went on forever. But anyway, there are two equations. Okay. Now, here's what Cramer's rule says to do. Okay? I think I'm going to erase everything else and just leave these two equations and then rewrite them. Okay? Or wait. I'm just going to erase everything and just rewrite those two equations. The first one was y1 u1 prime plus y2 u2 prime is equal to 0, which we just pulled out of the air. And that made then y1 prime u1 prime plus y2 prime u2 prime equal f of x. Okay. Now, what Cramer's rule does it gives you a way to solve a system of equations using determinants. Okay? You all know what determinants are. Okay, Bill does. Not. We've done a little bit with them. Okay. Let me
It's kind of like you're substituting
right.
what it looks like is you're substituting with agents.
Yeah, that's exactly what you're doing.
Yeah,
Let's come up with something else. Let's just say, give me a number, any number. 4. Give me a variable, any variable.
C.
Say again?
C. X.
Okay, X. Okay, I couldn't hear what you said at first. Plus or minus?
Plus.
Plus. Give me another variable.
Y.
Variable. I'm sorry, a number. 2. Y equal some other number. 8. Okay, I'm going to change that to 2x plus y is equal to 4. Is that okay? All right. Now, yeah. Give me another number.
6.
6x plus or minus? Minus. Give me another number.
3y.
3y equal?
8.
8. Okay, that will stand by itself. Now, we know how to solve this using elimination by addition, right? We could just multiply this equation by 3, and that would give us 6x plus 3y is equal to 12, right? Okay, and this would add them together, you get 12x is equal to 20, and x is equal to 5/3, right? I'm doing it fast in my head. 4 going, yeah, that, okay, got it? And then you could go back to either equation. I like the first one better, and this would be 10/3 plus y is equal to 4. Is that right? That would be 12/3. So y is equal to 2/3. Okay? So we know what that solution. Here's what Kramer's rule says. Okay? Kramer's rule says take the, now remember these are our first two equations. Okay? X is equal to, I'll do the denominator first. It's the determinant of the coefficient matrix. 2, 1, 6 minus 3. Y is something over, same thing. 2, 1, 6 minus 3. Okay. Now, what are the numerators? The numerators for the x is plug in the constants rather than coefficients. So that would be the determinant of 4, 1, 8 minus 3, and this would be 2, 4, determinant of 2, 4, 6, 8. That's what Kramer's rule says. Let's see what we get. Determinants, you do the down diagonal, so x is equal to minus 12, minus the up diagonal, which would be 6. Is that 8? No, it's an 8. Okay. Minus 8 over the down diagonal here, minus 6, minus 6. Okay? Which would be minus 20 over minus 12, which is 5/3. Oh, they got the same answer there. Okay? Here it would be down diagonal. Y is equal to 16 minus 24, right? Over, same denominator, minus 12. Don't have to do that again, right? Okay, so this would be minus 8 over 12, minus 12, which would be positive 2/3. Yep, we got the same answer. So that's what Kramer's rule says to do. Okay? Okay, now, what we have here is, goodness gracious, I'm stiff. These are like your variables. They're the same, like your x's and the y's, right? And these are like your coefficients and your constants. Okay? So let's do Kramer's rule with that setup. Now, do I need to leave anything here, or you remember well enough how to do Kramer's rule? Erase it all? Okay. All right. Trying to remember Kramer's first name. Gabriel, maybe? Seems like that's right. So if you needed a paper topic here, would be okay. All right. So variable u1 prime is equal to the coefficient matrix, but you put 0 and f of x here, and then you put y2 and y2 prime there, right? Divided by your coefficient matrix, which is y1, y2, y1 prime, y2 prime. Determinant of that, okay? Your u2 prime should be determinant of y1 prime, 0 f of x over, no, that's a y2 prime, sorry. Yeah. The same determinant. I'm not going to write it again. Okay? So this would be, that one's 0, minus this. u1 prime is equal to minus y2 f of x over, and this would be y1 y2 prime minus y2 y1 prime. Agreed? Plus, y2 prime would be y2 f of x minus 0, okay, over the same denominator, y1 y2 prime minus y2 y1 prime. Okay. I'm getting dizzy here. Okay. Now, goodness gracious, eyes just ache from straining this much. Need more light. Okay. Our denominator is y1, y2, yeah, got that right. The w1, which is the numerator for u1 prime, is 0, y2, yeah. And y2 is, oops. Sorry, so the 2's there, they're 1's. Yeah, those are y1's, not y2's. Sorry about that. Okay. Okay. Sorry. Okay. All right. So then these functions, u1 and u2, these are all things you knew. y1, y2, y1, y2 prime, y1 prime. We know them all because those are what they were given to begin with. So, and we know f of x. So we can plug all these things in, take a derivative of each side, and get what u1 and u2 is. Okay? This is y minus y2 f of x over that w. That's what they call w. And this one is y2, no, y1 f of x over that w. Okay. Why did we call those w's, or why did he call them w's? The determinant W is recognized as the Wronskian of y1 and y2. And if you remember the Wronskian, you put y1, y2, y1 prime, y2 prime. Okay? That was the Wronskian of the y's, the solutions for your homogeneous case. Okay? And by linear independence of y1 and y2 on that interval I, we know that the Wronskian of y1, y2, this one right here, cannot equal 0 for every x in the interval. Okay. Now, summary of the method. Usually it's not a good idea to memorize formulas in lieu of understanding the procedure. However, the foregoing procedure is too long and complicated to use each time we wish to solve that. So to solve a2 y double prime plus a1 y prime plus a0 y equals g of x, first solve the complementary function. First, find the complementary function, and then compute the Wronskian of y1, y2. Now, what I don't understand is where they got a2 and a1 when those were, if I'm not mistaken, variables. They should be a2 of x and a1 of x, shouldn't they?
I don't see A1 or A2 anywhere in the whole. Oh, here it is, the very top of the page.
Yeah. And don't they have x's with them?
They do have X.
Yeah. So they were supposed to have x's. Okay?
Good news is it's time to go.
Yeah. So let's pick up with example 1 next time. We'll try to use this that we've just done and go from there. So let me put a mark by example 1. Okay? And
Easier ones.
what's that?
They're going to be easier once we put
Some numbers in them and quit using letters and variables and stuff.
Big stuff I can't.
Right. Exercise 4.6. Since we haven't done a single example yet, we can't really do any of those yet. You can start looking at them with that example if you want to. If not, work on those tests and papers and get them in, and we'll pick up and go from there next time. We'll finish 4.6, hopefully. I don't know if we need to do Cauchy-Euler equation. I'm trying to recall if we've done those in the past, or Green's functions. Frankly, y'all have gone further than most classes go.
It was a 15-minute lecture on what the course, you're all about this hose.
Okay.
Some say I just want to know.
Yeah.
Okay, vessel function, course, you're all just.
Yeah.
Just to know what they were trying to do.
Right.
Because I know for next year I've spent all this time busy going over this stuff.
Okay.
So you all got wives and all that, you can stay busy.
Yeah.
Because you all got to do the honey-do routine, right? Honey-do this, honey-do
Yeah.
that.
Exactly. Yeah. I don't think we're doing 5 at all. I'm trying to see if there's anything else that you really need to know more than that. 5 review. I don't think you need 6 either. It seems like the next thing is Laplace transforms.
That always pops up all the time.
Yeah. So I'm real tempted, once we finish 4.6, which won't be too long, okay, to let's just, I don't remember anything about Cauchy-Euler or Green's functions. Green's function shows up in Cal 3, and we're not going to get to them there. That's why I was wondering if we should do anything there. But maybe just start talking about Laplace transforms, and because that's something I know was mentioned in the course description. So let's just move on to 7 after we finish 4.6. Basically, your final, I could give you right now because we've just done, well, once we finish 4.6, everything that's on your final. And I won't put any Laplace transforms on there, but we'll go over those just for your cultural enlightenment. Or either of you going in, well, I don't think Bill is, electroengineering? Okay. I don't know, you know about Corey?
I think he's doing mechanical.
Mechanical. Okay. I think you use Laplace transform way more in electrical than you do the others. Maybe some places, mechanical covers so much stuff. What are you going into?
Not sure yet.
Oh, yeah. Are you a pre-pharmacy?
Oh, mechanical.
Oh, you're doing mechanical. Okay. So it covers so much of everything, you might need just at least to know what Laplace transform is. So let's just hit that. As far as we can get, after we finish 4.6, we'll do as far as we can in 7. We won't get that far, I don't think, because these examples are going to take possibly a little time. It's example 1, example 2, and example 3. So, we'll see. Okay. We'll give that a shot. Good deal. I asked this before you came in. Have you seen anything in emails or anything about student course evaluations?
Yeah.
You have? Is it fairly recent? Because I'm behind in email, so it may have come out, but as of last week, I asked somebody and they hadn't seen any. So it must have come out recently.
Oh, that's Jeff's thing, sorry.
Oh,
I got it from Liv.
see, we should have had them a long time ago, and I haven't seen any word about them. I asked my boss, he said, I got to ask the dean about it, so I don't know if he ever asked her, but I saw her once in our meetings, I think on Tuesday, and I forgot to ask her then.